So in this video, what we are covering is just more details on those intermolecular forces. So we're just going to go through each of them and really explain them well. So the first intermolecular force that we're really going to look at are the London dispersion forces. So London dispersion forces are the weakest of the intermolecular forces. Dispersion forces, so these forces happen between all molecules, no matter whether they're polar or nonpolar. But what we will see is that there are stronger forces with polar molecules, so these really only become important with nonpolar molecules. The electrons around the atoms or molecules are in constant motion in every molecule, and they're not always distributed symmetrically around the nuclei. They move constantly in an electron cloud. At an instant of time, there can be a temporary or instantaneous dipole, which means that there would be more electrons concentrated on one side of the molecule and less on the other side of the molecule. So if you look at the picture on the right, you will see what I am talking about. On the top picture right here, you can see that those small circles are standing for electrons, and we know electrons are way smaller than that, right? But you can see that there they are, they're swimming around the molecule, and they're sort of distributed evenly throughout the molecule. But just because electrons are in motion, at some time, maybe more electrons are on one side of the molecule than the other. And that's what's happening here. And we can see that there's lots of, let me get a different color. There's lots of electrons over here. So that's why that side of the molecule for one instant in time is partially negative. And the other side of the molecule, because it has less electrons, is partially positive. And then when atoms or molecules are very close to each other, the electrons in a molecule with a temporary dipole, like what we saw in the picture right above, can distort or disturb the electrons in another molecule's electron cloud. So this is called an induced dipole. The temporary dipoles are only maintained for an instant, but that instant for an attraction, these temporary dipoles are only maintained for an instant. But that instant of attraction can affect the chemical properties of nonpolar molecules. London dispersion forces are sometimes called instantaneous dipole, induced dipole. And we can see this in the pictures over here. So here is that same carbon dioxide molecule. It's a nonpolar molecule. But for this instant, a lot of the electrons are on the left-hand side, which means that this side of the molecule is delta negative, is partially positive. While electrons are negative, so they're going to be attracted to that side of the molecule. So you can see that what has happened, it has induced. Induced is a word that means to make happen. It has induced a dipole on the other molecule. Now that molecule is sort of polar for an instant, and that can then induce a dipole on yet another molecule. This is the only force of attraction that there can be between nonpolar molecules. So you may think this is ridiculously weak. This doesn't really have any, can this really have any effect? Well, any nonpolar molecule that is a solid or liquid at room temperature, this is the only thing that's holding it together. So although it is the weakest, it can be very important. And then down bottom, you see that we can talk about, well, which molecules have stronger London dispersion forces? And larger molecules, specifically ones with more mass, so not really physically size, but the ones with more mass have stronger London dispersion forces. This is because their electron clouds, they would have more electrons because they are larger. The electron clouds are what we call more polarizable, meaning that the temporary dipole is more likely to form. And because the temporary dipole is more likely to form, the London dispersion forces are stronger. The shape of a molecule can also affect how these London dispersion forces act. So if two molecules are about the same mass, but one of them is longer, so maybe shaped more like a straight line as opposed to like a circle, that would also be more polarizable. So therefore it would have stronger London dispersion forces. And you can see the example over there, chlorine to chlorine. So this molecule is very similar to the bromine molecule. The only difference, right? They're both linear, they both have the same hybridization. The only difference is that bromine has a lot more electrons. Because it has so many more electrons, the electron clouds are more polarizable in bromine. And you look at its boiling point. It is actually, almost 60, 70, 90 degrees higher than the boiling point in chlorine. It makes it so that bromine is actually a liquid at room temperature, while chlorine is a gas at room temperature. So again, although these London dispersion forces are thought of as quite weak, they can actually make a big difference. So this picture here is just another picture that shows you what is this idea of an instantaneous dipole. Right, here's the instantaneous dipole because just of the uneven distribution of electrons. This is actually in a helium atom. If you think, can an atom be polar? Well, if all the electrons, helium only has two, but if those two electrons are on the left hand, let's say these are the two electrons. If those two electrons just happen to be on one side of the atom for a second, it is, instantaneously at that instant polar. And then that can induce polarity in a nearby helium atom. And that can cause those helium atoms to then be attracted to each other. We're going to see that only happens at really low temperatures. Is that attraction actually strong enough to make it like into a liquid? And we already talked about this. The more electrons make the atom or molecule more polarizable and increases the strength of the London dispersion forces. So now let's talk about dipole-dipole interactions. So these occur in polar molecules where the molecule is polar 100% of the time, not an instantaneous dipole, but 100% polar. And so molecules with permanent dipole moments, which means that they're asymmetrical, there's more electrons on one side than another, are also called polar molecules. And in a sample, when polar molecules are present, the oppositely charged ends of the molecule attract each other. And these are called dipole-dipole interactions, right? Because it would be a polar molecule is attracted to another polar molecule. Samples with these polar molecules experience dipole-dipole interactions. They would have higher boiling points because this attraction, so this is looking at this is the attraction between, right, hydrogen sulfide, that would be the name of this molecule. The negative end of the sulfur, right, the negative end of this molecule is the sulfur end. It would have two lone pairs of electrons on it, and sulfur is more electronegative than hydrogen. And so the electrons kind of pool up here. So this side of the molecule is negative. The hydrogen side of the molecule is positive. And those two, those sides are always attracted to each other. So therefore it would take a lot more energy to overcome those attractions because they would be there all the time, as opposed to with London dispersion forces where they're only there for an instant. And then this is, of course, similar to, but not the same as, hydrogen bonding. So you can see the one on the left shows dipole-dipole interactions. And you can see the negative end of one is attracted to the positive end of the other, right? The positive end of one is attracted to the negative end of the other. And that's the exact same thing that we see in hydrogen bonding. The negative end of one side of the molecule is attracted to the positive side of another molecule. But in hydrogen bonding, those molecules are more polar. And because those molecules are more polar, the attraction is stronger. So this is our strongest intermolecular force. So in a sample, a hydrogen already bonded to an oxygen, nitrogen, or fluorine, and it's important because it's only these elements. in one molecule can have a very strong dipole-dipole interaction with an oxygen or nitrogen atom in another molecule. This is called a hydrogen bond. Remember, it's technically not a bond, but it is a very strong intermolecular force. The hydrogen bond interaction is particularly strong because the hydrogen's bonded electrons are pulled so strongly towards the covalently bonded oxygen, nitrogen, or fluorine atoms, and that is because they are the most electronegative atoms. Substances that have hydrogen bonding in between their molecules have a higher boiling point than the ones that don't form hydrogen bonds. So you can see here is the hydrogen bond. It's just an intermolecular force of attraction between the positive end of HF and the negative end of HF. Because hydrogen is so, let me erase that. Because hydrogen is so small and those three elements are so electronegative, it's, kind of think of it like those electrons are only spending maybe 10% of their time around the hydrogen and almost all of their time around the oxygen, nitrogen, or fluorine. And it just makes those molecules so much more polar than like the H2S and the HCl that we saw on the previous slide. That these molecules that have hydrogen bonding are just have much stronger intermolecular forces and have even higher melting and boiling points because it's going to take more energy to overcome those intermolecular forces.